With this screencast, we'll wrap up our introduction to organic chemistry and conclude chapter 10. When I first started teaching chemistry a long time ago, we never taught polymers at all. And as I was teaching, I don't know, maybe 10 years in, I moved to St. Louis to teach at Westminster Christian Academy after 3 years in the public school. And shortly after that, there were some possibilities for teaching polymer chemistry in the high school. And I went to a few workshops, and people would begin to say, here's a demonstration you can do about polymers for a high school class. And of course, it's become bigger and bigger. And now it's a completely separate discipline within the field of chemistry and within the subfield of organic chemistry. Your whole focus can be on polymers. In fact, your doctoral degree and your sole research might be just a particular polymer. Well, of course, you know that the word polymer has the word poly in front, even though it looks like poly, and the girl's name is Polly, but it's pronounced poly, and you recognize the ending of the word mer because we have isomers and we have monomers and dimers. And of course, the term mer means parts and poly means many. And basically what we're doing is we are putting small molecules or smaller molecules together in big, long chains. And those chains can sometimes be a single chain with no branches. Sometimes there can be lots of branches. Sometimes there are what are called cross links between parallel polymers, which make the polymers very, very strong and rigid. So that's amazing all the different things you can do with polymers. And of course, as you might suspect, polymers have existed naturally ever since God created plants and animals. We didn't realize that organic chemistry, of course, was invented and imagined and created by the Creator. And so we think about polymers such as wool and silk. We think of polymers like proteins and DNA and carbohydrates. Cotton is a polymer. So there are all kinds of naturally occurring polymers. And once again, we find ourselves kind of thinking God's thoughts after him, to use a phrase by Johannes Kepler, the famous astronomer and devout Christian. So these polymers can be synthetic, which means we make them in the laboratory. They are, of course, naturally occurring. And sometimes once we figure out what their structure is naturally, we go to the laboratory and see if we can duplicate that in the laboratory. We can also make polymers that, as far as we know, don't exist naturally. All of those would be synthetic polymers. Now, moving to the other parts of the stuff that I have highlighted in yellow. All this chemistry we're talking about is probably mostly within the last 75 years, certainly less than a century. It wasn't until nylon was invented as a synthetic polymer that this field really took off and we began to realize all the possibilities. So be that as it may, 1976 was when polymers became more abundantly produced than steel itself in the United States. And that is a big landmark change. There are different ways that you can categorize or organize the thousands and thousands of polymers that there are. You can organize them according to what happens to them in response to heating, such as thermoplastics and thermosetting plastics. The thermoplastics are the ones that get soft and then they flow when they're heated, and then they harden when they're cooled. Thermosetting plastics, if you look at that word setting, they also will get soft and will move around, and then when it cools and it hardens, that's it. They are set in place and they cannot be resoftened. So that would be the difference between a thermoplastic and a thermosetting plastic. And of course, the word plastic itself just about invariably means we're talking about a polymer. Another way of categorizing polymers is, what's their application going to be? Are these polymers being made to become plastics, like plastic bottles and plastic toys and things like that? Or are the polymers going to be used to form fibers like you might find in clothing and carpets? Are they going to be turned into elastomers? And you should be able to guess what those are. That would be a category of polymers that are elastic, that can stretch and come back again. Then we have polymers that are coatings, and we coat them on things maybe to prevent them from oxidizing and rusting, or maybe to give them some type of surface that has some color to it, protective surface. And then you've got polymers that are adhesives. And it's amazing what you can do with adhesives. Imagine trying to build things and construct things and so forth more than 100 years ago, when there really wasn't any such thing like, well, there were some rudimentary kinds of glues, but you didn't have glues and you didn't have tape and adhesives like that. Now, another category of polymers are the addition polymers. Addition polymers, and you might remember we talked about addition organic reactions in the previous screencast. Addition polymers are polymers where you take your monomers, your single units, and when you put them together, you add them together to create a longer structure that has the properties that you want. Now, oftentimes, when you add two polymers together to make something that has a mixture of the properties of those two original monomers, it kicks out a small molecule like water, and that would be a condensation polymer. It condenses out the water. Another word you've heard me use for this would be a dehydration synthesis. So let's focus on addition polymers, because this is the way chemists usually look at them. Business people or industrialists, manufacturers would look at their applications. So addition polymers, and there's a whole table of these on page 475, which we'll get to in just a little bit. And let me show you a very, very simple way to make a polymer. Polymers almost always begin with ethene, and the old-fashioned name for ethene is called polyethylene. Just ethylene. Ethyl is the old-fashioned prefix for two carbons, F. And I'm going to draw my hydrogens like this, out of position. Should be trigonal planar around each carbon, but you'll see why in a minute. If I take another ethylene molecule like this, and if I have the right catalyst and the right temperature, I can break the double bond, leaving behind a single bond, which immediately frees up carbon to create two bonds, one on each carbon. And if the first monomer and the second monomer come together, and they're just one bond, each carbon has an octet, and I can put another one here and another ethylene here, and on and on and on, thousands and tens of thousands of ethylenes in a row. So that's a good example of making probably the simplest of polymers, polyethylene. So I'll write the word polyethylene here. And that's why ethene or ethylene is such an important compound to produce, because then it can be shipped all over the place and then it becomes a precursor for many, 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 many other kinds of compounds. So when we refine petroleum and separate it into its fractions, the mixture into its fractions, and all of those fractions can have an application and a purpose, you see why ethylene is one of the top 5 chemicals produced in the United States. Now, before we move on to the next page, here's a picture of some of your types of polymers. Picture A, high density polyethylene as opposed to low density polyethylenes. Think of the different kinds of plastic. Some of these plastic containers are quite rigid, and some of them are very, very soft and flexible. Think of a 2-liter soda bottle. It's much softer and flexible than the containers that you see here. Polystyrene. You take a styrene substituent and you substitute that in for one of the hydrogens. So you have 2 carbons with a double bond between them and a styrene attachment. And we'll look at one a little bit later. And then you polymerize it, means you break the double bond so that all these monomers stick together, and now you have polystyrene or styrofoam. And then polyvinyl chloride, especially these pipes. Where would the Blue Man group be without these types of PVC pipes? Polyvinyl chloride. And so there's a vinyl chloride attachment. So you take your ethylene, knock off the hydrogens, stick a vinyl chloride on there, and then polymerize it, and now you have PVC. And of course, all of these things eventually have to be shaped into their function. So we come over here in the next page. There we go. And I mentioned this already. You can have linear forms of polyethylene. You can have branched, which makes it sort of a lower density and therefore softer and more flexible. And then as soon as you have one polyethylene and another polyethylene and you cross-link it, and you kind of get rungs along the way, this becomes Cl, cross-linked polyethylene, and that becomes even harder and more rigid than the high-density polyethylene. So how do you do this? Well, one thing is you have to raise the temperature above the boiling point of water. That's not too difficult to do, but look at these pressures. If you consider that the pressure right now, average atmospheric pressure, is just 1 atmosphere, we're talking 1,000 to 3,000 times greater than that in order to create this polymerization process. Another way of displaying a polymer is to use the letter N, where N can be any whole number you want of these ethylene molecules concatenated together end to end in big long chains. Maybe you can recall the child's toy that has these handheld plastic tubes that have little knobs at the end on one side and a hole in the other, and you can connect them together and make things out of them. Well, that's what we're doing with polymerization. Another way of doing this is to show your ethylene molecule in the condensed structural formula and stick the letter N to show that it repeats on and on and on. A polymer it's not unusual for a polymer to have a mass of 1 million atomic mass units, or 1 million Daltons. And a polymer, and when you have a million like that, 36,000 ethylene molecules linked together are going to give you that molar mass of about 1 million. And of course, there's polymers much longer than that. As the structures as you substitute different things in for the hydrogens, you get different properties, and those properties then can be very important in terms of the application that you have in mind. Catalysts often involve transition metals, and again, they have high temperature but very high pressures, especially when you want to cross-link them together. And the high molar mass chains have a density that's just about the same as the density of water, just a little bit less than the density of water, which means they will float, not dissolve, of course, because they're nonpolar. And notice the abbreviation for a high density polyethylene. It's hard and it's tough. If you have branches, it's not as hard and tough because the branches keep it from being as dense, so it's a lower density. We're down to 0.92 instead of 0.97, and it's much more flexible. And we would use it for the plastic wrap and the sandwich bags and so forth. And then when you cross-link it, then it becomes really rigid and flexible. Think of a very hard bottle cap. And again, this reference to table 10.12 is coming. So here's how you make your polyvinyl alcohol, for example. In this case, you have your CH2CH2 with a double bond, and you're going to knock off this hydrogen, and instead you're going to put a hydroxyl group in there. And then when you break the double bond, now you can have bonds on either side. And over here. And then you can make a polymer with your ethylene. Here's your polyvinyl acetate, where we have a vinyl acetate, which is the oxygen right here connected to both this carbon and this carbon on both sides. It's kind of like an ester. Whenever you have a double bonded oxygen and a single bonded oxygen on both sides inside a carbon chain or interrupting a carbon chain, remember that's an ester linkage because that's what esters are. Here is your styrene, a phenyl group right there, resonance structure. And you've knocked off a hydrogen, you've put this in its place, and then you polymerize it n times. So here's a good summary, and you're not going to have to memorize what makes something a propylene. Well, you should know ethylene, you should know propylene. Vinyl chloride is where you use a chlorine substituted in for hydrogen. Propylene or propene, the technically correct name that no one uses. Notice you have carbon, carbon, carbon. So there's your propene. And it's like you've substituted a methyl in for a hydrogen. And then when you break the double bond, now you're going to get a structure that's going to look like this. And we're going to polymerize this. We start off with a double bond and a methyl group that's attached, which makes it propene or propylene. And then when we break the double bond at the right temperature and pressure, and now they can connect side by side and get big long chains, you have polypropylene. Vinyl chloride, PVC pipe, we've already talked about that. Most of your modern houses use lots of PVC pipe. You will not have to memorize what is a acrylonitrile, like in nitrile gloves, if I remember correctly. But in this case, you have a cyanide placing a hydrogen, and then you polymerize it. For styrofoam, you stick a styrene in place of a hydrogen. For your polyvinyl acetate, in adhesives and textile coatings, you have this structure right there. Remember, this part here would be an ester linkage, which I mentioned earlier. You won't have to know what acrylate is. But the acrylate is going to be having both a methyl and this acrylate on substituting in for two hydrogens. And then down here, Teflon coating on a fry pan is when instead of 4 hydrogens, you have 4 fluorines. And so it looks like this if I draw my fluorines out of position for the sake of the point. Make another one right here. Whoops, nothing there. There. And then I knock off or break the double bond, so I only have a sigma bond there. And now I have room for carbon to continue to have an octet, but it bonds out to the side. And then you polymerize it in big long chains. You have Teflon. In fact, it's not unlikely that if you look at the surface of a Teflon-coated frying pan, you have maybe 1 or 2 molecules of Teflon, where the molecule of this Teflon is millions and millions of monomers long. Now, my favorite one is Kevlar. And Kevlar was invented by a lady working for DuPont, I believe. She became very, very famous by doing this, and she worked in chemistry all of her life. She just was very, very good at it. Even she didn't start off pursuing chemistry, but then that's where she ended up. And I appreciate her because I appreciate Kevlar, because my oldest son, who's a police officer, has to wear a Kevlar vest. And unfortunately, with the super high-powered weapons that the bad guys have these days, Kevlar, for some of those weapons, doesn't have the stopping power. But you can look up the history of Kevlar. So now you know how we do these polymers. Now there's a key word here called hydrolyzing. And hydrolyzing is going back a little bit the other way. When you take a polymer and you're going to knock off its functional group. So hydrolyzing means to react it with water. So however many of these molecules you have of the original polymer, however many monomers you have in the original polymer, you need the same number of water molecules, and you knock off this COOH, which remember looks like this. I keep drawing it this way because I don't like the O2 in there. And you're going to get N of those and N of those. So this would be a hydrolysis reaction. You might also have seen this demonstration done. You can certainly see it online, where styrofoam, of course, does not dissolve in water because it is nonpolar. But it will dissolve in a nonpolar solvent like acetone. And you can put hundreds of these styrofoam peanuts in there, and they will all come down here into the solution. Now, fewer and fewer companies are using styrofoam for their packing peanuts, and many of the packing peanuts now are made out of starch. Well, starch is a little bit polar, and as you can imagine from the starch food that you eat, starchy food like bread and rice and potato and pasta, you can dissolve the starch peanuts in water. Another very, very interesting history is to study the role of rubber, natural rubber, and then finally our ability to make it in the laboratory so we didn't have to rely on getting it from trees in equatorial regions, rubber trees. Way back in 1740, a guy named Charles McIntosh, back actually in 1823, rubber was first introduced in 1740, but he figured out a way to put this on cotton cloth, and it became a raincoat, often called a Macintosh in Great Britain. It was still kind of tacky, and I don't mean that as a fashion statement, but kind of gooey, especially if it was really warm. It just wasn't really great. But then Charles Goodyear comes along, and with a few modifications, he's able to turn it into a substance that is elastic and water repellent and resilient and no longer sticky. and he used sulfur in order to do that, which of course paved the way for making automobile tires, which in the early 1900s were becoming very, very popular. And you recognize that Goodyear is the name of a very famous brand of automobile tires. This is a demo that is sometimes done in middle school or in chemistry classes in high school, making slime, which is this, it's called an aqueous suspension of polyvinyl alcohol. And it's kind of like silly putty, only it feels a little bit watery, wetter, gooier. And when they were first introducing polymer chemistry to students, they had them make slime. I remember going to a workshop for teachers to make slime so we could teach our students. Here's your formula for rubber. It's a diene, so there's going to be two double bonds. Where are they located? Off of carbons 1 and carbon 3. So it's going to look like this. Carbons 1 and carbon 3, butadiene. And then you're going to have a methyl group off of carbon number 2. And it often goes by the name of isoprene, which would be your isomer of an isomer of a 5-carbon diene, pentadiene. Vulcanized rubber is because of that sulfur, and it caused the polymer to become cross-linked. And we mentioned before that makes it super strong, super resilient, and which is what you need for automobile tires that are going to get very hot when you drive for hours and hours on an asphalt road in the middle of July. It does not undergo permanent change, and it springs back when you bounce over a pothole or something like that. And so we can call it an elastomer because it's somewhat elastic. We mentioned that a lot of times you can get your stereoisomers of cis and trans polyisoprenes. And this is one of the few cases that I know of where the chemists at Goodyear managed to figure out a way using a special catalyst to prepare all cis polymers and not the trans polymers, because it was the cis polymers that had the desirable properties. Now, a lot of times we polymerize something by putting different monomers together. One kind of monomer connected to another kind of monomer. So you're going to need a pressure, temperature catalyst that can break the double bond of both of the different monomers in order to make a copolymer. And again, we make a billion kilograms of this stuff in the United States each year. And believe it or not, some of this polymer is used in bubble gum, which makes it nice and chewy over a long period of time. It's funny, they also can use that to make automobile tires and other things made out of rubber, like rubber hoses. So I would suggest you don't swallow your bubble gum. And I've already mentioned condensation reactions as when you polymerize some monomers and it splits out or spits out or eliminates or squeezes out a small molecule, such as water, and we're making it a dehydration synthesis. There are other small molecules you can squeeze out besides that, like, let's see, I would think ammonia, probably c10, cyanide. And here they tell you your book cover, assuming you bought your book, is a copolymer, making the rigid structure of the cover of your book. Well, I'm sorry, not the cover of the book, but the picture that's on the cover of the book. And of course, the all-important toy, Legos, made out of what we call ABS plastic, which is a copolymer of 3 polymers, acrylonitrile, styrene, and polybutadiene. And Legos, of course, a very important toy. My boys grew up playing Legos, and we still have boxes of these things in the house. And now I have a grandson that likes to play with Legos, and maybe another grandson in a few years who will like to play with Legos. And sometimes my three boys, maybe it's Christmas or Easter, and they're all over the house, they'll go down in the basement, pull out the Legos, and here you have a bunch of 40-year-olds playing with Legos along with my grandson, which is pretty cool. All right, polyester. Polyester would be a polymer, and it would have an ester group. Here's your ester group again right there. Notice this carbon has both the double bonded oxygen and a single bonded oxygen to it. That's where the word ester comes from. And so you can take this kind of acid. You'll notice it's got the ester on one side and the ester on the other. And then you combine it with antifreeze or ethylene glycol right here, which has hydroxyls on both sides. And you end up with a structure that combines their properties. It kicks out a water molecule, so it's a condensation reaction, a dehydration synthesis. Let's see, that we make a lot of fibers for carpets and clothing this way. Maybe you have some things made out of Dacron. Dacron can also be used as a substitute for human blood vessels, or at least to give them some support if there's a worry about aneurysm, a weak spot in a blood vessel. Mylar, which we often have Mylar balloons, which is this polyester film coated with some polyester over that, and it helps to hold in the helium. And it's at the thickness, 1/30th the thickness of a human hair. Then you magnetically coat it, and you can also make audio and video tapes, which of course we don't use anymore. That day when we had reel-to-reel recordings and cassette recordings and video cassette tapes came and went very, very quickly. By the time I could afford those units, they were already obsolete. Down here, they talk about polylactic acid and another condensation reaction. And the interest in this is you can make it using the fermentation process and from plant material, which gives it the advantage of being green, in the sense that you're not using petroleum products. You're using plant matter. It's also supposed to be carbon neutral, which means you're not doing any chemical process that's going to release carbon dioxide into the atmosphere. And it's also biodegradable. As you know, we have lots of places where there are huge amounts of non-biodegradable plastics floating around when we didn't realize the mess that we were creating. In fact, there's regions in, I think, the Atlantic Ocean towards the equator where they've got a huge bunch of this stuff, and people are trying to come up with some engineering way to remove all these non-biodegradable plastics, especially from bodies of water and ocean floors. Polyamides. Remember, an amide is going to have that nitrogen in it, which is what the amines have, but it's also going to have the carbonyl, the double bonded oxygen. It makes it an amide. And you can take this adipoyl chloride, and I don't know if you saw this demo in honors chemistry or not. I've done this demo over here many times where it looks very, very, very gooey. And if you look carefully, this surface of the denser liquid at the bottom and the less dense liquid at the top, from the interface of these two liquids, these two different chemicals, where they are mixing together, a chemical reaction takes place. This chemical reaction right here is taking place at the interface. And if you reach down with a pair of tweezers or something and pull up this plastic, you can begin to wrap it around a rod or something like that. This is actually nylon 6,6. And the reason it's called 6,6 is because you have 6 carbons in your adipoyl chloride, and in your hexamethylene diamine, you have 6 more carbons. So it's called nylon 6,6. And I've made this before. The word that my students always seem to use is the word snot. It looks like really, really gooey nasal secretion. I don't think I've said that word since maybe last year. All right. Nylon, of course, it's stronger than natural fibers. It's chemically inert. It can replace silk and linen and wool and cotton, which are naturally occurring polymers that especially were needed, for example, in World War II for parachutes and so forth. This is a closer look at recycling polymers. Polyethylene terephthalate, PET. Let you read about that. Coming down over here, back to the nylon. This is why we needed to come up with a synthetic way of making nylon. It has good tensile strength. It's pretty hard to tear. A lot of that's because of the cross-linking again. We also talk about the hydrogen bonding, which we're going to get to in Chapter 12, as being a super strong form of intermolecular force when you have strong dipoles involving nitrogen, oxygen, and fluorine, which I sometimes call NOF to help you remember it. Here's another illustration of a condensation polymer, polyamide. Let's see. Over here, green adhesives, which are used in all kinds of different ways, including sometimes as a replacement for stitches when someone needs stitches. And you could probably practice on your own before you close out this screencast and check for your understanding. And that's our overview of polymer chemistry, which is a branch of organic chemistry.